In this video, we will be comparing linear versus nonlinear regression in Microsoft Excel using the well-known Michaelis-Menten kinetic expression shown here. In it, CS, or the concentration of substrate, is the independent variable and the reaction velocity V is the dependent variable. The two parameters, the maximum reaction velocity and the Michaelis constant, can be determined through nonlinear regression. However, it is also possible to linearize this equation and express it in these three forms, known as the Lineweaver-Burk, Eadie-Hofstee and Hanes-Woolf equations. Before we carry on, it is necessary to select the following add-ins under the Options menu. Go to Add-ins, click Go, and make sure that Analysis Toolpack and Solver are selected. Furthermore, also under the Options menu, under Advanced, you're able to set the system separator. In this case, I selected a decimal point. Now I've created the raw data by choosing different values of CS and then using 0.3 and 0.15 as parameter values. To this, I then added some Gaussian noise to emulate experimental error. Now it's a good idea to keep your raw data separate from your calculations in case something happens to it. So I'm going to copy these columns to a new sheet, and since we won't be using the exact values of the reaction velocity, we can delete them. I'll be using a data table to make the calculations a bit easier, but it requires that we remove any other rows that are not data beneath the headers. So to do that, I'm going to take the header rows and transpose them under the Paste Special menu to the README sheet. If you want, you can format the units by pressing Ctrl-Shift-F and then selecting superscript. Likewise, we can do that for the per hour value, or just use Alt-E, because that E is underlined as a shortcut to select the same option. Now that we've safely removed our units, we can get rid of this row and transform this into a data table by pressing Ctrl-T. Let's rename this sheet to Calculation. When we're doing a nonlinear fit, we want to assume values for our parameters that the solver must then use when minimizing an objective function. Typically, the sum of the square of the residuals are used. So, let's do that. We'll create some values that we're going to fit using a guessed value for Km and Vmax. For starters, let's just assume that both of these values are 1. Because we are going to be using both of these values in each one of the rows of the data table, we want to provide an absolute reference to these values. This can be done by using $ signs, such as referring to Vmax as $13, or alternatively by giving it a name. Under the Formulas ribbon, you can check Define Name, and it will automatically assign the value, the name that is next to it. So now we can type in our formula, which is Vmax times CS divided by CS plus Km. All of the values in the table then are completed. Let's visualize what this looks like. You can press Ctrl-A to select all of the values, then go to the Insert ribbon. Under the Charts tab, you can use this button to insert scatter plot. I'm just quickly going to format it. I usually remove the chart title because when we embed this chart into a report, the title is typically given as a caption below the figure. Furthermore, these grid lines aren't very useful and act like chart junk in this case. For the chart area, that's this part over here, I'm going to add in a border. But for the figure area, I'm going to take away the outline. Likewise, I'm going to turn these axes into black and remove the legend for the time being. If you double click the axes, this Format Axis tab shows up, and under tick marks you can select Major Inside to add them. Lastly, you can also add in axis titles. Now, because the formulas in Microsoft Word are formatted in the Cambria font, I like to use that font throughout documents as well. So I'm going to change this to Cambria and ensure that the text is black and change it to size 12. Okay, now before I add any further embellishments, I'm going to save this as a template. So you can right click, select Save as Template, type in scatter. So in future we can use this to format quickly. Now I just want to ensure that the numbers on the axes are typeset indeed as numbers. We can now type in the variable names on our axes. V, typically in italics for a variable, and CS. Now you'll also want to add in the unit in brackets, but just to save time, I'm going to forgo that for now. And legend. Now, typically to save space in papers, legends are typically boxed within the chart area. We can change their names over here, where series 1 will be our experimental data and series 2 is the fit. Because the fit is typically an equation, we want to display it as a continuous line and not as discrete data points, because that will imply that there are different measurements. So under change chart type, I'm just going to change that to a line. Now that we can see that our guess values are sufficiently close to the data values, we can use them as the initial guesses in our solving routine. But first we need to define an objective function to minimize. And in the case of nonlinear fitting, it's typically the sum of the square of the residuals. So what we're going to do is calculate the difference between our fit value and our data point and square that. We can sum this column by pressing Alt equals. And what we want to do is minimize this value. Another nifty trick is that we can use a built-in function to calculate the sum of the square of the residuals. So if you go to the formulas ribbon under math and trig, and you scroll down to sum xmy2, you can select the x array and the y array, doesn't matter which order, and it'll calculate the same value. Okay. Now, to solve for our nonlinear parameters, our objective is to minimize this value by changing the variable cells km and vmax. I'm not going to specify constraints in this case, but you can if, for example, one of the parameters must be greater than 0 or must be above or below a certain value. Alright, we can see that our calculated values are pretty close to the actual values that we used. Now let's compare this to the linear Lineweaver-Burk equation. So we're going to calculate 1 over CS and 1 over V. Now we don't want these plots on our graph, so you can just select them and delete them. The same thing goes for the SR plot. To generate the new plot, you can press Alt F1. Although this may not be the chart type that you're looking for. But you can go under Templates, select the one that you created earlier. We can further edit the plot to ensure that the right data are being displayed. So our X values are 1 over CS and the Y values are 1 over V. We do not want this column to be displayed by itself, so I'm just going to delete that. Lastly, we can now add in the variable names once again. Right. To add in a trend line, you can go to this tab, and to specify the equation on the graph, you can scroll to the bottom of this right tab and select the bottom two options. Okay. If you want, you can also edit the y and x values to be that which you have on your axes. Sometimes this will change back to the column names after solving. Okay, so we can see that we've got a pretty high coefficient of determination on this graph. Let's use it to calculate the intercept. Let's use its intercept and slope to calculate the parameters. So we can use the inverse of the intercept. To calculate Vmax, and slope times Vmax to calculate Km. And we can definitely see that the values here are quite far off. Nevertheless, let's compare it with the other two equations. For that, we will need V over Cs and Cs over V. Okay, so I've just cleaned up the spreadsheet a little bit. We can do the same for the number of decimal places being displayed. As you can see that we get different answers for our two parameters based on the type of fit that we chose to apply. Since we know that the true values, in this case, for the parameters are 0.15 and 0.3, and all of these values are below it, we can apply some conditional formatting where green is the best and red is the worst. We can see that the nonlinear Michaelis-Menten equation gave us the answers that were closest to the ones that we used to generate the data. From this now we can calculate the average percentage error because we have the true values. We can simply subtract them and express them relative to the true value. But in practice we won't have that luxury. So how then can we compare the fits?